All right, I am back, and we need to maybe look a little bit more carefully at solutions of differential equations and some of the things that can happen to them. We haven't done, we haven't spent a lot of time on this. We've almost always assumed that solutions just exist and it's never an issue. But that's really not the case. And I can illustrate that with this really innocuous looking differential equation, dx dt equals x squared. So it's really a very, very simple differential equation. With an initial condition, and initial conditions are important for this, x at some time t0 is equal to y0. And so what I'm going to do is I'm going to actually solve this differential equation. And when we solve the differential equation, we'll learn something from that. Otherwise, I would just tell you what the solution is. So let's see. So we would solve this by separation of variables. So we get dx over x squared is equal to dt. And then I would integrate this. And when I integrate that, I get minus 1 over x equals t plus c. Right, this is x to the minus 2, and the antiderivative of x to the minus 2 is minus 1, x to the minus 1 divided by negative 1, so that's where the negative comes from. Then we might use the initial condition. So I would get then, to use the initial condition, I get minus 1 over x0 is equal to t0 plus c. And then I would solve that for c. And so I get c is equal to minus 1 over x0 minus t0. And if I then I would take that value of c and I would plug it in here and I would solve for x. So let's just hold on to that c for just a minute. Now let's come over here and solve this for x. So when I solve that for x, I mean, because we now know what c is, just save me a little bit of writing. I invert that, so we get that x is equal to minus 1 over t plus c. That step was just really important right there. But I inverted that, and so now you can see I'm going to have an issue when t is equal to negative c. But then if I now put the initial condition back in, put that value of c in that we just got, not the initial condition, but put that mess in for c, and then simplify, I get x is equal to x0 divided by 1 minus t sub 0 minus t times y sub 0. Okay. So I do some algebra there. I just bothered to not show you. All right. So there is our solution to that initial value problem. And there's something I want you to note here, that t is undefined, or x rather is undefined. When the denominator of that fraction is equal to 0, or when 1 minus t0 minus t times y0 is equal to 0. Or when t is equal to t0 minus 1 over y0. That is undefined. So that tells us that there exists a solution, but the solution only exists for a finite amount of time. Well, it might not be finite. In fact, it's not in this case. Only for t bigger than minus 1 over y0. So it's not defined for all values of t, for all real numbers. It's only defined for some subinterval. That may be a finite interval. In this case, it's a infinite interval, but it's not from minus infinity to infinity. It's only from minus 1 over y0 to infinity. Right? But the point here is this, is that even a really simple differential equation, its solutions might be only exist for some amount of time, and that interval of existence can depend on the initial conditions, both the initial time and the initial point. This should be an x0, not a y0. I don't know why I wrote y0 there. That should be an x2. That should be an x2. Actually, I do know why I did that. That should be an x2. Let's add y in my notes. All right. So as I said, this illustrates one important aspect of the existence theorem. It is a local theorem. It's helpful to think of what to maybe just talk about another example really quick here. And again, I am going to erase this stuff. So if you need it, pause the video for a second and talk about another example. That looks very similar to that. 1 plus x squared. And I'm just going to give it an initial condition of x of 0 is equal to 0. This has no critical points because that's 1 plus x squared. If I go to solve this, I'm not going to do the whole solving here, but we get dx over 1 plus x squared equals dt, and then we'd integrate because of the 1 plus x squared business. I'm going to get an inverse tangent on the left, and then when I solve this, I get tangent for x. So I get x of t is equal to the tangent of t. The important thing about tangent is that it's not the graph of tangent. I'll do the best I can to draw this. I'm really bad at this. It looks like that. Has these vertical asymptotes, and they happen at pi over 2 and negative pi over 2. Because tangent is sine over cosine, and cosine is 0 at pi over 2 and negative pi over 2. And so this differential equation, its interval of existence, or this initial value problem, because I gave you an initial condition, its interval of existence is negative pi over 2 to pi over 2. So unlike the last example, this is we would say that this differential equation is a solution that exists for only finite time, just around that interval. And it would change if with a different initial condition. Right? I just picked that initial condition because it was easy. So this idea of local solutions is important. Right. This is a really important example because it illustrates something incredibly important about that there are differential equations that have non-unique solutions. And the example is this. X dot equals x to the 1/3 with an initial condition that x of 0 is equal to 0. So that's our example. We want to look at. All right, so let's see. One solution is obvious. There is a really obvious solution that we get without doing any work, and that is that x of t is equal to 0 is a solution to that, not just that differential equation, but to that initial value problem, right? If I take the derivative of that, I get 0. If I raise 0 to the 1/3 power, I get 0. So it satisfies the differential equation. It also satisfies the initial condition because if I let t be 0, x is 0, since x is 0 for all values of t. So that's the obvious solution. But I claim it's not the only solution. I claim that, here's another solution. And we can find this you can find this by doing separation of variables. Let's call this x1. Let's call this x2 of t. And it is 2/3 t all raised to the 3/2 power. I claim that that's another solution. So let's just check this. Let's check that that is indeed a solution. So there's two things that it has to satisfy. It has to satisfy the initial condition and the differential equation. Satisfying the initial condition, x2 of 0 is clearly equal to 0, so it satisfies the initial condition. The second thing that it has to satisfy is that it has to satisfy the differential equation. So that means I would take x2 to the 1/3 power. So that 1/3 came from there. That is equal to 2/3 times t to the 3/2 to the 1/3, which is equal to 2/3 t to the 1/2. Right? Because I have 3/2 power and a 1/3 power, that gives me a 1/2 power when I multiply those. So that was just plugging into the right-hand side. On the other hand, the derivative with respect to t of x2 is equal to, so you got to use the chain rule for this. So I get 2/3, that's the derivative of the inside, times 3/2 times 2/3 t to the 3/2 minus 1, which is 1/2. And lo and behold, we got the same thing in both these spots. Those are equal. And that is a problem. I now have two differential equations that satisfy the same, or two solutions rather, that satisfy the exact same differential equation. I will try to draw a picture as best I can of what is happening here. We have one solution that I'll draw in red. This is going to be x1. It's the solution x, so let me label my axes. Here's t, and there's x. So back to here. So here was one solution. That's x1. What is x2 look like? Well, it sort of looks like that. It is, we'll do that in blue. It's going to be this, but it only exists from here to the right. That's I'm sorry, it is that. It's that 2/3 t to the 3/2. Now you'll notice that this runs into a problem when t is less than 0, because if t is less than 0, then I can't take its square root. It turns out one can fix that simply by defining x2 of t to be 0 when t is less than 0. So one can actually make it then continue along like that. It turns out that there's other solutions as well, like minus this quantity. So we could put a negative sign in front of x2 and we'd get a solution, right? So what went wrong here? Well, I'm going to give you a clue as to what went wrong before I stop this video. And the clue is, think about x to the 1/3 and its differentiability. When I take the derivative of x to the 1/3, I get 1/3 x to the negative 2/3, and that in particular is undefined when x is equal to 0, right? So we run into an issue when x is equal to 0 with the differentiability of the given vector field, right? And so that's important for the existence and uniqueness theorem. All right, so just to quickly summarize, I've given you an example of a first example that we talked about on the previous page of differential equations that have solutions, but those solutions only exist in finite time. That's going to show up in some sense in the existence and uniqueness theorem, but actually in the conclusion. Then we looked at an example of a differential equation, x dot equals x to the 1/3, where we didn't actually have uniqueness. We had multiple solutions to the same initial value problem. I said, but you don't have to believe me, that the problem is because this function, the vector field, is not differentiable at x equals 0, which corresponds to the initial condition. And that is going to point to a hypothesis of the existence and uniqueness theorem about the differential equation itself. So, so when we get back, we're going to start talking about, in the next video, about some of the tools needed, I guess, to prove the existence and uniqueness theorem.